would like to have someone else who, in addition to Alan, as you can see he's not here today, who would like to learn more about videoing the program so that we can spread it out. So if you have any abilities, any interest or whatever, please contact myself or David. And so, and today, it's about relationships. According to Mailen, God is relational within and without. Where there are no relationships, there is nothing. We do not have relationships. We are relationships. Relationships matter and matter relates. Mailen is working on a book called The Tree of Complexity, How the University is Built from Relationships. He has a doctorate from Brown University in Providence, Rhode Island, and he served as a professor, researcher, administrator at Andrews University, Duke University, and Loma University. He has published 5 book chapters, more than 60 scholarly papers, and many more abstracts and reviews. And again, I would say he's in the process of writing his book now, and is out for, not editorials, but for comments. And his comments, his scholarly interests are truly relational. They include physiology, pharmacokinetics, biomedical engineering, computing, and religion. He's an accomplished musician. And David says that some of the words which come to mind are balance, moderation, creative, thoughtful, and calm. And so, are we we're almost ready?
I don't have the notes here, but we'll go with it.
Okay. Anyway, again, Mailen, I've known him now for about 5 years, and I find him a very interesting person. But as I mentioned the last time, the most important thing I could say about him is he likes cats. And so at this time, I'm going to have Mailen come up and are you on there with that microphone?
Am I on? Can I be heard now?
Yeah.
Good. Thank you. And thank you to the class once again for giving me time to come and speak with you. Sorry we're having a little technical problem. Last week I brought my own computer and that didn't work quite right, and this worked. Today this is not working quite properly. But we'll do the best we can with it. Since this is part 2, I need to open with a brief review of what we talked about last time. I suggested that as we're interested in how humans view the universe they live in, has gone through 3 phases throughout the known human history. First phase, the description is really very simple. God or gods control everything. The weather, the crops, reproduction of your flocks and herds, and it was humans' job just to please the god or gods. And we get this information, of course, not only from biblical record, but from paleontology, archaeology. Phase 2 was a period of about 2,000 years, beginning roughly with Plato's ideas, and it summarized briefly as the great chain of being concept, with God at the top of this hierarchy, angels below, further look down, humans in cultural order with kings and rulers at the top, wealthy people, ordinary people, the poor and destitute, and then below that animals also layered, then plants, and finally the rocks. The scale of that chain of being is soul, with God 100% soul, and rocks being 0% soul. I'm most interested, and today we'll spend all of our time on the modern era. I just introduced my main idea last time, so we'll proceed right on to that. I'm calling this the Tree of Complexity. It is a hierarchy, but not a command hierarchy. There are 2 types of hierarchies. This is a a hierarchy of constitution, of content, not of command, like the military or business. And if you look at the items here at the bottom, we have the smallest things that we know, the simplest, nuclei and nuclear particles, atoms, and then you can follow up the chain here. Atoms put together make organic or inorganic chemistry. Organic chemistry makes biochemical reactions. Biochemical reactions, you put them together and you get cells and so on. So this is a tree of complexity. It's obviously very simplified. There could be many other layers and names tucked in here, but that's not my point to be complete. But I do want you to pay attention up here. Humans are part of this tree of complexity, and human activities, in other words, human-to-human relationships and groups, just as we have atom-to-atom and cell-to-cell relationships down below. And this list over here is not meant to be a hierarchy. It's just a partial list of the kinds of things that humans generate when they come together. Now, I introduced a word last time that's probably not so familiar to most of you. That word is a holon. And this word is used to describe an object at any layer, any level of this hierarchy. And why is a special word chosen for that? Why not just call it an object or a member? Because in this kind of hierarchy, those objects have very special properties. Number one, an object, and we're talking about an object at any one of these levels in the hierarchy, it's a whole. It can live by itself if it's in the right environment. So we say it has agency. It can also be a part. That is, it can be joined with other holons to create something new. When it loses its agency, it self-dissolves into subholons or holons at a lower level. And when it joins with others, we call that synthesis or self-transcendence, because it generates something larger, more complicated, and with new properties. And we also use the word emergence for that. Now, what I want to do is now look at some ideas that come out of this tree of complexity. What can we conclude about a variety of things? And this is going to be the basis of most of the other ideas I talk about. In this tree of complexity, the key idea to take home, if you don't remember anything else, relationships in this hierarchy are the important concept. The entire universe, including humans and human activities, can be described as a hierarchy of levels of complexity, each level consisting of components from a lower level interacting. The structure of the universe is thus based on relationships and interactions, or its relationships all the way up or down. Now let me give you a quick little illustration to show you what I mean. Everybody in the room here knows that you're made of electrons, protons, and neutrons, right? You don't have to be a nuclear physicist to know that. So let's suppose that I could disassemble you today. So we now have a pile of electrons, and a pile of neutrons, and a pile of protons. Each one of those particles is in its own pile is absolutely identical to all the others. It has no identification on it where it came from or what its history was. It's absolutely pristine. So my question is, what has happened to you? All these particles formally made up you as a person, a human being. The fact is, you could not be identified by any of those particles in any of those three piles. You are made up of those particles, yes, but in a specific set of relationships, which are really defined by the tree that I've shown you there. You put the atoms together to make chemistry, chemistry together to make cells, and so on. So it is strictly the relationship of all those parts that defines you, not the particles themselves. Now, the next thing I'd like to do is to say something about the relative maturity of the research and the thinking in the various levels of this hierarchy. And in order to do that, I need some kind of scale, and here it is. I'm giving it to you all in one slide rather than breaking it down in steps. Level 1 is naming things. When people start doing research in any field, this is where they begin. They name the phenomena that they see and hear and observe. They next group those phenomena together, things that are alike. Next comes a higher grouping. For example, naming below, you might recognize hawks, or a kind of hawk. You next recognize that there's multiple kinds of hawks. That's level 2. Level 3, you recognize that there's other kinds of birds than hawks. There's also hummingbirds with multiple kinds. So you now say, what is the possible relationship between hawks and hummingbirds? That's level 3. Level 4, you begin to think about, why do I have this structure? What is my initial theory as to how this might come about? That is, you begin to form a model, and the first level of model usually is a physical one. I've shown one kind of physical model here, not for birds, but for the our solar system. It's called an orrery, and it's a mechanical device that roughly approximates at least a portion of our solar system. The sun's in the middle. You see the Earth there on the right-hand side with the moon around it. And if you turn the crank on this orrery, these objects would rotate around. They're not to scale, of course, because the differences in size are much larger than they are on that little machine. But at least the larger ones are larger and the smaller ones are smaller. And they go around in orbit roughly in the same order of time, although not exactly to scale. So that's a mechanical model or a physical model. There are many other kinds. Even a drawing on a whiteboard is something I would call a physical model. In chemistry, there are ways of describing chemical reactions and so on. The final level at the top is another kind of model and a mathematical model. And I've just shown one equation here to represent that. Why is that at the top of the heap for research maturity? Mathematics is the thinking tool of scientists. It's a tool that allows scientists to be very specific about what belongs in a theory, and then to ask what the results are from that theory. In the mathematical modeling, what is done is to first write an equation that represents a relationship. Here comes that word again. That equation, such as the one here, and let's maybe move to the next slide to show you where that one comes from. This comes from a very simple model. I call it the leaky bucket. It's a bucket with water or liquid in it. We measure the height, h, and there's a valve or a hole down below that the water flows out. And what we would like to know is, how long does it take to empty this bucket to a given level? And so we write an equation representing the relationships there. I don't have time to go into the math of it, but the point is that that equation comes from a couple of physical laws. Those are, number one, the conservation of liquid. Whatever liquid disappears from the bucket comes out down below. It doesn't disappear in the middle. The same amount of liquid always exists. The second one is that gravity acts on the liquid in the bucket, and that's what causes the pressure at the bottom of the bucket, forcing the liquid or the water out of the bucket. So those two laws are the basis of this relationship. Now, the other point I have to emphasize is that relationship equation doesn't tell us the answer we really want, which is the behavior of the system. That's what we're interested in. How long does it take to empty the bucket, or to a certain level at least? To find that out, we have to do what mathematicians call solving that equation. Now, there are two ways of going about that. One is to look up the equation in a table to see if mathematicians have worked out a solution for that particular equation. It turns out for this simple one that I have used here, they have in fact, and we could look up that equation and get our answer directly. But almost none of the interesting problems in the world can be solved that way. You can just about forget about what you learned in beginning calculus, other than understanding what calculus is about. You have to find a solution a different way. That way can be done by hand, or it can be done by computer. By hand, what you're essentially doing is following the behavior of that relationship equation step by step, tiny time increment by time increment, just as in fact nature does. Now, for a simple problem like this, that's not much work. We can generate a table of answers like this and see the results from the leaky bucket. But real-world problems don't have just one variable like the height. They might have tens, hundreds, thousands, or even millions of variables. So this now comes down to a lot of handwork, a lot of manual labor to build tables like this for 100,000 variables, let's say. We'd have to have that many tables, and we'd have to take each one of them down the line step by step. If any of you have seen the recent movie called Figures, the group of black women who was working for NASA at the time were doing exactly this. NASA had no computer at the time, and in order to plan the directions of the satellites and the paths, they had to go through this very tedious step-by-step process. Now, during the time that the movie portrays, NASA did get a computer, and the women shifted over to becoming programmers instead of doing the work by hand. But one of my main points here is to emphasize how important it is for scientific theory to be able to solve equations of this type. Everything that we have come to love, from not only the space program, but all of the semiconductor work that makes the phones and other nice devices that we have possible, all requires very sophisticated computations. And I'll put it very bluntly, if the computer had not come along in the mid-20th century, scientific theory would have virtually ground to a halt. Because there's no other way to think clearly about scientific research other than mathematics, and if all of this had to be done by hand, we would be progressing very, very slowly indeed. What did people do before there was this kind of computation available, and what can we say about the maturity of the fields in this hierarchy? Well, one thing we can say is, as we move higher up on the tree, that means by definition higher complexity, bigger calculations, and more difficulty. Now, what did people before computers, what did they do for theory? Well, let's take medicine, for example. What did the medical doctors, what did the physicians do before there were nice theories about physiology and pharmacology and so on? Accidental discoveries of herbs, folklore, theories not based on experiments like the Greek idea of the 4 humors in the body. I'm sure you've probably heard about that. That resulted in some treatments that actually harmed people rather than helping them. But the physicians at that time, up through much of the 19th century even, was still being treated by bloodletting. And the idea of vitalism was alive and well through much of the 20th century even. This is an idea that says that all living things have a kind of spirit. That spirit is not related to the material that they're made of, but it's something totally separate. And as I say, that idea survived well through much of the 20th century, I'm sorry to say. How does the scientist come up with the appropriate ideas for theory? Well, there's a process for that, and it's called reduction. That is, you take the object that you're trying to study, the holon at whatever level you're studying, break it down into components or subholons and the relationship between them. So here's parts and pieces, here's the interconnection pattern between them. So you have reduced the holon that you're trying to understand to something simpler. Now, the question is, how far down do you need to reduce? This process of thinking about natural mechanisms for any kind of scientific object being studied is called naturalism, and there are basically 2 kinds. One, ontological naturalism. A person believing in that feels that they must reduce all the way down to a fundamental level, not just 1 level or 2, but to the bottom of what is known, or even farther, hopefully, to some base level. Unfortunately, the tree of complexity that we know now doesn't really have any bottom. It's holons all the way down. People are, of course, thinking about string theory and various other things, but even that may not be an actual root of that tree. But nevertheless, there are some very vocal scientists, a few, who try to make it sound as though they're truly ontological naturalists. Another part of that belief is that there is no such thing as supernatural. Now, the other kind of naturalism is methodological naturalism, and it has 2 significant points. One is that to do useful science, you don't have to go all the way down in reduction. Reducing by 1 or 2 levels is adequate, because in science we don't try to get final causes, final answers for things. We're looking for practical understanding that can benefit humans, and that's the goal. To accomplish that, 1 or 2 levels of reduction is adequate. In addition, for methodological naturalism, the supernatural is not permitted in theories. Now, that is not to say that the supernatural does not exist. But it's not permitted in theories because as soon as the supernatural is inserted in a theory, research stops in that area. It's the universal solvent that fixes everything. And as we'll see in a few moments, our understanding of what can be described by science is limited. And so we really do not do ourselves a favor by coming to a halt just when we get puzzled and don't think we can go any farther. Next question I'd like to ask is reduction it? Is that the basics and all there needs to be done in scientific research? No, there's another process which is the opposite of reduction, and it's called synthesis, where we take bolons and put them together to generate something new. It's the opposite process. Now, when should synthesis be used? Although it's not typically done, I'm suggesting that synthesis should always follow reduction. That is, when you take a system apart to figure out how it works, when you get your disassembly, your subholons, you should always use synthesis to put them back together again to see if you didn't, make sure you didn't break something when you took it apart. You should be able to get the same answer that you measured in the first place. And I just throw this up here as one very early example in biology, biomedicine, where that was done well and deservedly a Nobel Prize. People in understanding the operation of the nerve cell and how it generates its action potential, which is, this is a recorded one down below. Some very clever experiments were done using the large nerve cells from the giant squid, large being about the size of a very small pencil lead. They measured multiple ion currents, which are represented by this electrical circuit diagram. That was their reduction. Now, they then took the equations describing those currents and solved them to do the synthesis again. And this upper chart here is the result. The two are obviously a good match, and you should understand that top one is not a curve fit. It's not something they twisted a knob or something to get it to look right. It was actually generated directly from the breakdown that they had done in understanding the independent ion currents. So that's a perfect example of how research should be done and well deserving. Just want to remind you that synthesis is creativity in any field, not just in the scientific laboratory, but in construction, in sculpture, in visual arts, music, in the classroom, the work of writers, and many others. I wish I had time to just talk about creativity here this morning. It's a fascinating field, but we'll move on. Synthesis, bottom line, is creating complexity with a purpose. Now, one more thing that I will have to say about synthesis here. This is the process of synthesis. We start with polons of relationship, write the equations that represent how that works, and solve those equations. But there's two things that are important to remember about that process. One is that the properties of what is created, that is the new behaviors of the new system here, are not predictable from the properties of the holons that were put together to make the synthesis. That is, we get new properties over here when the system is put together. And that's why the word emergence is used, and that could be a topic of a whole presentation itself, which I don't have time for. The second thing that is important is for anything on the table, on the tree that I've shown you, higher than an atom or so, the number of possibilities that you can get just by putting one group of holons together is virtually infinite. Let me give you an example. If you put 20 carbon atoms together, people have calculated that you can do that in something like 366,000 different ways, 20 carbon atoms. If you up that to 40 carbon atoms, the number now becomes 62 trillion possibilities. Now that's still a pretty simple system, 40 carbon atoms. In our DNA, we're talking about billions of carbon atoms in one DNA molecule. So you can see that the number of combinations is really just numbers that are beyond imagination, which means we cannot ever explore all the possibilities that occur when we put pieces together in this tree of complexity. People are very interested in why some things show up and others don't seem to show up in nature, and are thinking about why that might be. So there's really a limitation of science that comes out of this. There's virtually infinite number of possibilities that can be synthesized at any level of the hierarchy above atoms. We can't explore all possibilities at any level. There are just too many. We're thus limited by current technologies in deciding whether or not any given observation is or is not a natural event. Therefore, our ability to judge whether any event is natural or supernatural, meaning outside of natural laws, is limited by the known technologies based on the known previous history of observations. So it behooves anyone thinking about science to be very humble in terms of trying to judge something as a supernatural event. Now let's look briefly at some of the things we can say about the human groupings up here. And I'm going to have to go through this very quickly. When you put humans together, because human communication is so varied and so powerful in many different ways, we get all sorts of things. These are just a sample of the kinds of things that happens when you link humans together as holons. All the way from families and tribes, which seems natural, to governments, scientific research, business. People are very interested in altruism, and I'm going to have to really just skip right through this, because the prevailing theory, being evolution, has as its basic mechanism dog-eat-dog type of mechanism, grabbing what you can get. But as a matter of fact, there is substantial amount of cooperation and altruism in nature, and some of the thinking about that has been given the name game theory, not that it's really a game just to play, but it's a way of thinking about interactions, whether they're positive or negative. And out of that has come a golden rule for evolution: cooperate at the first step and then reciprocate after that. Another area that I find very interesting, especially in our own day right now, is the idea of social capital, which has something to say about how humans relate. Social capital means a level of reciprocity, trust, and cooperation in society. A very famous sociology paper from the 1990s was part of a large controversy about social capital. And the interesting thing that came out of this was that the things that society really desires, that is economic prosperity and many other things, quality of public life and so on, is a result of social engagement, not a product thereof. In other words, you might think superficially that as long as people do well economically, they would trust each other and behave better, but it's exactly the opposite. When they're trusting each other and working together, then in economic prosperity and all these other things shown in this last paragraph here come along with that. Now, just a couple of things about religion. That's one of the activities brought by people coming together. Our late colleague, Dr. David Wilbur, wrote a book in which he listed these 9 benefits of religions. And you can see what they are. They're social cohesion, that is a group to belong to, making meaning, existential relief, meaning a promise of some continued existence in the afterlife, and so on. The question is, how are those benefits achieved? And certainly within the Judeo-Christian area, we have it spelled out in a way that exactly belongs in this tree of complexity that I've shown you. When Jesus was asked, what's the most important point of the law? What did he say? He described 2 relationships, man to God and man to man, or human to human. And this is not only a New Testament idea as well, it's an Old Testament idea. The 10 Commandments are also 2 sets of relationships. Religion is a complex human system, but just as in the rest of this tree of complexity, relationships are important and are key. The nature of those relationships can determine the outcome. In the religion systems, any kind, rituals and beliefs usually come from a founder or founders, and they're only rarely modified afterward, as a rule. Can we apply any of the ideas of research to religion? I think generally that has not happened. I would suggest that there is an opportunity for religion here to have a look at rituals and beliefs to see if they are in fact producing the kinds of results that religion would like to see. And there are in fact beginnings of some research projects. A project out of Norway, the University of Agder, are studying exactly that. The difference, of course, is that in religion, the evidence is always personal and private, as opposed to public evidence in science. That means that we do not get the uniformity of belief in religions. In fact, we get great diversity of belief because the evidence is not public and common. It is so very personal. Personal selection of religion is strongly influenced by environment, meaning the culture, the family, the environment that they grew up in. So that's all the time I really have to talk about this tree of complexity and relationships. I will look forward to your questions, and once again I thank you for the opportunity of coming here and making a presentation.
Okay, Mailen, I'm sure there's no questions because we absorbed all of it here.
Right.
Okay, any questions? I recognize the gentleman in the back here.
Thank you for this, Mailen, and thank you for our breakfasts with Forrest and others every Friday morning, right? Those breakfasts started in 1990, and they continue every Friday morning. So thank you for being a part of that and a wonderful soul. I really like the partial shift from competitiveness to collaboration, second shift from analysis to synthesis, and then also from ontological non-theism to methodological. Okay, 1, 2, 3, I'm with you. I want to push back against the idea that all the evidence religion has is private. I'd like to suggest that it has some public evidence as well, as in this little tiny suggestion. We have been told that by some that it's okay to handle venomous snakes, and one will not be bitten, or if one is bitten, one will not get sick and die. But I think the public evidence strongly suggests otherwise. What would you say to that?
Well, I tried to hint to that directly. I should have said it more loudly, but when I say I think religion has an opportunity for doing this kind of reductive research, that would require public evidence. Otherwise, it wouldn't make any sense. So I agree with you. I just didn't say it as clearly.
Mailen right here.
Mailen, when you're talking about your models,
Yes,
and you said the highest level was math,
yeah.
don't you think there's an area for abstract thinking, that there are some abstract thinking or thoughts or ideas that really can't be reduced to math, and probably will never be reduced to math? And so, you know, is in your hierarchy, is there another level there that should exist?
Abstract thinking without the precision of mathematics is otherwise known as intuition. Okay? Intuition is extremely unreliable. It feels really good, but it's not useful really in the long term. Mathematics, the benefit of mathematics is it forces you to be as precise as you can be. Now, that doesn't necessarily mean that you always have to include every possible known factor, and that's part of the job of the modeler, to try to understand which factors are important and which to leave out. My career, some of you know, was research on heart muscle, how it works electrically. And there was a member of the group that I worked with who was a world expert in the cellular structure of heart muscle. He had looked at hearts of every size, from hummingbirds to whales. So he knew a lot about heart structure. Now, if we put too much of that structure in, the computation got too big and we couldn't do anything. We were just stumped. So our job was to try to figure out what were the important factors, and it really forced us to think about that clearly, whereas intuition frequently failed us. So that would be my answer. I think still math is the top of the heap. Yes.
Thank you so much. I have two, along with Dr. Larson's idea, there are two variables in research for religion. One is the social justice idea that I think we can observe. I don't know about coming up with a mathematical solution. Right now, the prosperity gospel, you know, we have the saying that do what God tells you and you will prosper. Well, it's not really leading to justice. And so there are models that we have that if you do whatever God pleases, He will bless you with wealth. And that's very popular right now. But there are a lot of people who are doing good and they're not well. So I think there's something we need, we can look at. And another one is social justice. What is going on with our faith and religion, and all religions, I mean Christianity or Judaism, or, you know, in practice, is not working really well for justice. So is there a way that we can think of developing models of that? Because you were talking about probability of possibilities of thinking and putting variables in. It is hard.
It is hard. I've made a career of doing that, and even in the physical world it's hard, never mind the relationship between humans. But I think the bottom line is the result of whether it be government or religion or family or whatever it is, the results do depend on the nature of the relationships. And the best that we can do is to help people understand that. If they want good results, they have to be willing to work in a cooperative mode and not grab as much as I can get mode, which seems to be very popular right now. That's the message I think that religion has to say, but there needs to be some evidence of it within the religious group.
Thank you for your presentation. When most people think of relationships, we think of something that's dynamic. There are energy flows, there's give and take, there's secretive, there's growth, and yet your model seems relatively static. The tree symbol is in fact a dead tree, and I'm wondering if in your concept and your thinking here, can we ever expect to see leaves on this tree? Is the tree going to have roots? Will the tree be embedded in soil? Will it become animated? Will it be a living tree? Or are you just focusing here on kind of a constructive, observational model? But can we expect to see life in your tree of complexity as it is in real life? And riding on the back of that is science and research, as you know, is meant to move a body of knowledge forward, either for the science population or for the general public or some given population. What one or two things do you think this model really contributes to us and to the field of knowledge? How is it advanced? Just give me one or two. Thank you.
To answer your first question, I tried to communicate the fact that this is a growing tree by talking about synthesis, because that's what the growth is. New things come out all the time, and that's the way they come about. So people who are creative are people who understand the creative process, how to put things together to get something new. So this is a growing tree.
Yeah, life is in the synthesis.
Life is in the synthesis. We need to do reduction to understand the particular level we're working at as best we can. But ultimately, the goal is also to work back through synthesis to get something new or understand, produce something new. Now, let's see, your second question.
What are the just one or two main takeaways
Oh.
that you'd want us to appreciate from this body of research that you're presenting?
Well, I think the very idea that I'm a little bit biased here because my career is in computer modeling, but that is becoming so widespread now as a way of investigating new ideas. I think that is based on the whole tree idea of increasing complexity and synthesis. And I happen to, I don't know if many of you are aware of the service called Google Alerts. You can send Google a little short phrase or a word, and they will then automatically send you every day whatever has been added to the World Wide Web with that phrase in mind. So I have a Google Alert for computer simulation, and I'm now getting probably 20 items a day of things that are new being done with this, new areas of understanding, development, and so on by using that method. So I'd say that's making a big contribution now that couldn't have been done a couple of decades ago.
Thank you.
Yes,
Thank you, Mailen. To illustrate your chain of relationships, in your first presentation, you gave us a timeline. And you mentioned a few people, Plato, with his theory of forms or ideas.
right,
You mentioned Aristotle, you mentioned Plotinus.
right.
But you didn't mention Jesus Christ, and I was a little surprised because you didn't find a role in your diagram for him. At least as it is related to the humans and societies in all that list that you presented there. You didn't find really a role for Jesus, or is just an omission
Well, I was primarily tracing how humans relate to the natural world they live in. Now, Jesus, in my opinion, did not come here to teach us about that. He came here to teach us about relationships. And I did introduce that, I hope, forcefully enough, in this part of the presentation.
Well, you mentioned
Yeah.
about the commandments.
Right, which is the very key idea. Jesus said that's the most important thing. Now, during that middle period, the Christian church was very much involved. It was very much involved in supporting the philosophical ideas that came from Aristotle and others, not only about behaviors and so on, but also about the universe, the cosmology and everything else. So I didn't go into that. I don't think that's something that Jesus came to reveal, personally. Yes?
In your first presentation, you began listing some of the common characteristics of the Neolithic period.
Yeah.
In fact, that could be expanded just a little.
Right.
But that is typically a prelude discussion to intelligent design. You came to the cusp of intelligent design and backed away from that, and backing on what my colleague over here said. Was that intentional? Do you see that your model could, irrespective of our belief in God and Christ, at least cross that threshold into intelligent design, which is where this whole presentation seems
There's
to go?
two levels of intelligent design: lowercase ID or uppercase ID. I firmly believe in lowercase ID. I think there is design in nature, and I'm a believer in God. I think God originated. But the uppercase ID is a particular movement that tries to prove the existence of God. That I do not agree with. In fact, I indirectly spoke against that by saying as soon as you introduce God as the final argument in your scientific understanding, you have stopped doing science. So I think the uppercase ID movement is not a good thing. It's not a positive thing. It doesn't speak well of God either, in my opinion. I think by thinking of the vast opportunity for creativity here gives a much broader and more creative picture of God than the so-called intelligent design movement. Yes.
In the world we sort of inhabit here, there's often drawn a distinction between faith and science, a very antagonistic relationship, as though one, if you go with one, you can't go with the other, and, you know, at least 6 days a week, and then you switch for one day to cool off and then go back. Could you see with your model that if we abandon the ideas of the words science and faith or religion and came up with a new process word or an idea, that you might find a better way to get together rather than this unholy sort of thing that we have going at the moment?
Well, one of the things that I hope to make a little contribution to by describing this structure is to show, number one, that what we call science, which is primarily things below, at the human level and below, including ecologies and so on, and the human groupings are part of the same hierarchy. This is not two different worlds, but they're part of the same universe, number one. Second, I hope to communicate the idea here that people who do work at the upper levels, I'm not talking about the galaxies now, but the upper levels of complexity, which are really here, the human interaction, are working with much more complicated systems than even the most complicated cells and organs down below. They're vastly more complicated. So I think the area of religion deserves some sympathy for that. In other words, it should not be knocked down because the science is not as precise as it is for the simpler systems down below. I'm trained as a physicist, so I learned mathematics as part of my field, but in biology, this is relatively new in the last few decades. So do we disparage them because they were so backward? I'm trying to communicate here that they had more complex systems than the physicists had to work with, so I have sympathy for them. And I think that should expand even more to the human groupings, because there the systems are vastly more complicated yet. That's what I'd like to contribute out of this.
Mailen, I'm going to give you one more minute. Is there something you would like to leave with us here? I mean, obviously this is new, and I know you want to get back to your cats, but cat, or you're down to one.
The only thing I would say is some people might look at this diagram and say, this looks like evolution, progressing from the simpler to the complex. I'd just like to point out that this is not the case. This is not directly connected with evolution. People who believe in evolution for other reasons would say, yes, this would fit that. But this is simply a description of the way the universe is structured now. And whether you believe in God, believe in fiat creation, or believe in God that creates in a different way, all of that can fit within this. That is, you can still pay attention to this hierarchy and learn from it in any of those cases. I chose not to talk about the origin of all of this because it's too big a subject and we're not giving me any time for anything else.
Okay, thank you very much. Just to mention, we do have bulletins here on the desk. Don't forget the Winiger awards this afternoon. And next week, Zach Plantak will be with us. And we'll have our benediction at this time. The Lord bless you and keep you. The Lord make his face to shine upon you and be gracious to you. The Lord lift up his countenance upon you and give you peace. Amen.